Hello everyone. In this lecture I want to sort of summarize some of the main aspects of dealing with a general system of m equations in n variables with a matrix approach. Okay, so let's start with a sort of a general setup, some nomenclature to organize a whole bunch of equations in a whole bunch of variables. So we'll suppose that we have m equations in n variables, and the n variables will be x1, x2, up to xn. And here is a system of those m equations. So let's read this. The first one is a11 x1 plus a12 x2 plus all the way up to a1n xn equals b1. So that's the first equation, and notice that the coefficients of the a's, they all have the first index equal to 1, corresponding to the first equation. The second index corresponds to the variable name. Once we understand that, then the second equation makes it a little bit more, even more clear. So we have a21 x1 plus a22 x2 all the way up to a2n xn equals b2. And we have m such equations down to the final one, am1 x1 plus am2 x2 plus all the way up to amn xn equals bm. So that's a bit of a mouthful, but that captures a general system of equations. And I want to emphasize that the relationship between m and n is not specified. So m could be equal to n, m could be less than n, m could be bigger than n. Okay, then we've already seen that to organize this kind of data, we can organize all the coefficients in a matrix A, and here it is right there. So we're just putting all the entries together in a systematic way. And we might point out that in this story here, Aij is the entry in the ith row and jth column. So for example, this entry here is in the mth row and the second column. The other ingredients we need are the vector x, consisting of just the variables x1, x2 down to xn, and the vector of numbers on the right-hand side of the system, we're calling that b. That's vector b1, b2 down to bm. So those vectors are not the same size. A is an m by n matrix. X is a n by 1 matrix or vector. And B is an m by 1 matrix or vector. And then the whole system is equivalent to the single matrix equation A times x equals B. And in order to sort of make that work, we need to have a notion of matrix multiplication that explains what the matrix A times this column vector x equals. And I just remind you that the definition involves sort of two steps. So this involves kind of matrix multiplication, where we first define the product of a row vector with a column vector by this formula here, which is really essentially a dot product. And then once we have the product of a row vector times a column vector, by the way, of the same size, crucially, those two vectors have to be the same size, then we can define the product of a matrix with a suitably sized column vector. So here on this left-hand side, we have a matrix, and here is a column vector, and if the number of columns in the matrix equals the number of rows in the vector, in other words, if this dimension here equals this dimension here, then we can multiply those two things. And we do so just by using the formula that we've just established by taking products of rows times column. That's the first entry. And then the next row times this same column. That's the second entry, and all the way down to the mth row times again the same column gives us the last entry here. All right, so that's how we defined multiplication. And that then allows us to give proper meaning to this matrix equation AX equals B, which captures the in matrix form the system of equations. Okay, so that was the notation, so just a quick summary. And now we want to just summarize what we ended up doing with row reduction. So what we do is we create an augmented matrix for this system. So we put the matrix A and the vector B together, and we can sort of record that in this fashion. So this is the matrix A on the left, then there's a vertical bar, and then the column vector B. And then what we do is we row reduce this thing, row reduce, to get an equivalent matrix, say of the form U, say Y, which is in reduced row echelon form. And it's at this stage then that we can deduce various things about the solution to the original system by looking at this reduced row echelon form of the augmented matrix. And so let's summarize the kinds of things that we've been talking about for this augmented matrix. So theorem, first of all, if Y is a leading column of this augmented matrix U, Y, then the system has no solutions. On the other hand, if Y is not a leading column, then there are solutions. And maybe that's the first point. And the second point is that if there are solutions, if solutions exist, they are described by parameters, where the number of parameters equals the number of non-leading columns in U. Okay, so the U and the Y both have roles to play. First, we look at Y. If that's a leading column in the system, then there's no solutions. If that's not leading, then there are solutions, and the number of parameters in a solution is the number of non-leading columns in U. So as a consequence of that, as a corollary, if U has only leading columns, and Y is not leading, then there's a unique solution. There's a unique solution to the system. Another way of saying this, so equivalently, another way of saying this is that every variable is a leading variable. Every variable is a leading variable. Because remember, the variables themselves correspond to the columns of the matrix on the left-hand side. Correspond to the columns. And so if all of those are leading, then there are no non-leading columns. And then we have the solution. So if every variable is the leading variable, and maybe we should, and Y is not leading, still have to have that condition. Okay, great. So I want to now also give another kind of consequence of this, where we look at the relationship between M and N. Okay, so let's say if A is an M by N matrix, which can be row reduced by our elementary row operations to say U in row echelon form. Then the system AX equals B has, okay, there's a number of possibilities. First of all, at least one solution, for each B in Rm, precisely when U has no non-leading rows. And I'll say the other one. The next one is at most one solution for each B in Rm, precisely when U has no non-leading columns. And exactly one solution for each B in Rm, precisely when U has no non-leading rows and no non-leading columns. Okay, so let's understand why this is true. So we're looking at this general system, and starting with the matrix A, which is m by n, we've row reduced it to a matrix U. And we're kind of interested in the equation AX equals B for maybe general values of B. Like maybe we're looking at this system with lots of different values of B, and we're concentrating on the matrix A. What properties of A or its row reduced form U will ensure various things. And the first statement is saying that when U has no non-leading rows, then there will be at least one solution for each B. So the reason why you do not get a solution is because as we've seen, the last column, the Y column on the right, it ends up being a leading column. That's then giving us a row which has all zeros up to this last entry, which is non-zero. That's the reason why there's no solution. Now that'll only happen if the matrix U, which is in row reduced form, has a row of zeros at the bottom. In other words, that's a non-leading row because it doesn't have anything non-zero in it, in U. So it's the condition of such a row of zeros that will mean that there's at least one vector B that you can cook up that will guarantee that there's no solution. So we have at least one solution for any B precisely when U has no non-leading rows. In other words, there's no rows of zeros in it. On the other hand, if U has no non-leading columns, then if there is a solution, there has to be at most one, because we know that the number of parameters corresponds to the number of non-leading columns. And if we sort of put these two things together, then we have exactly one solution for each B precisely when U has no non-leading rows and no non-leading columns. So every row is a leading row, has a leading entry in U, and every column has a leading entry. So that's kind of a general encapsulating of a lot of the different possibilities, starting with the matrix A. Okay, so the last topic I want to talk about is linearity. And this is an important feature, of course, of linear algebra, because it's all about linear things. And it's really captured by the linearity of matrix multiplication that we've defined so far. So there's a fundamental rule that if we take the matrix A and we multiply by the sum of two vectors x plus y, then that's the same as A times x plus A times y. That's one of the linear conditions. And the other linear condition is that if we take the matrix A times, say, some multiple lambda of x, that we're getting lambda times ax. So these are the crucial linear properties of multiplying a matrix with a vector. And I want to illustrate this just to give you an example. Okay, so suppose that we have, for example, 1, 2, 3, 4, 5, 6, okay, and we're multiplying it by the vector x1, x2, and I'm going to add y1, y2. So this is going to take this combination, okay? So here's the matrix A, there's the vector x, there's the vector y, and here's x plus y. So this is going to be, say, 1, 2, 3, 4, 5, 6 times the vector x1 plus y1, x2 plus y2. So that's how you add vectors. And then when we do this matrix multiplication, what are we going to get? Well, this is a 3 by 2 matrix, and this is a 2 by 1. So we're going to end up getting a 3 by 1. How does that look? So it looks like 1 times x1 plus y1 plus 2 times x2 plus y2. Okay, we're taking the product of this row times this column. And that's the first entry of the product. The second entry is obtained by taking the second row times, well, the same column. So that will be 3 times x1 plus y1 plus 4 times x2 plus y2. And the third entry is obtained by taking the third row by the same column, and that's 5 x1 plus y1 plus 6 x2 plus y2. Great. Okay, now we can, however, rewrite that as x1 plus 2 x2, 3x1 plus 4x2, 5x1 plus 6x2, that vector plus the corresponding vectors in y's. y1 plus 2y2, 3y1 plus 4y2, and 5y1 plus 6y2. Okay? Remember, we add vectors component-wise. And once we've done that, we see that what's on the right-hand side there is a times the vector x plus a times the vector y. And the other law, a times lambda x equals lambda ax. That can also be illustrated in the same kind of way. Suppose that we have 1, 2, 3, 4, 5, 6, and we're taking our vector and say multiplying it by lambda. Okay, so lambda times x1, x2. That's going to be 1, 2, 3, 4, 5, 6 times the vector lambda x1, lambda x2. When we do the matrix multiplication, we're going to get 1 times lambda x1 plus 2 times lambda x2, 3 times lambda x1 plus 4 times lambda x2, and 5 lambda x1 plus 6 lambda x2. Now, strictly speaking, I should really put brackets around here because that's really the order that we're doing it in, isn't it? Okay. But because inside here there's just numbers, we don't actually really need the brackets. And so we could rewrite what's inside there as lambda times x1 plus 2x2, and then lambda times 3x1 plus 4x2, and lambda times 5x1 plus 6x2. And once we've done that, then it's obvious that that's just lambda times the vector x1 plus 2x2, 3x1 plus 4x2, 5x1 plus 6x2, which is lambda times a times x. Okay, so we have verified, this example, this second linear property. Okay, so these two properties are very important, okay? They are sort of at the heart of linear algebra. They occur in many, many different contexts. And when we start talking about matrix multiplication more generally, these same kinds of properties are going to be happening there, okay? So the kind of thing, so that things are maintained when we look at sums of things, and they're also maintained when we look at scalar multiples of things. Now, what consequence does this have for systems of linear equations? So this has some consequences. So let's have a look at a rather special kind of system. Solutions to a system of the form AX equals 0. Okay, so this is a special kind of system where the right-hand side is 0, sometimes called homogeneous system. Okay, that's the terminology. Homogeneous, because the right-hand side is just 0. So what can we say about such a somewhat simpler system? Proposition that the vector x equals 0 is a solution, no matter what A is, for any A. And that's completely obvious, because if we take the matrix A and we multiply by the 0 vector, we're going to get 0, because all of those products are 0. So it's immediate. A somewhat less trivial thing about one of these homogeneous systems is that if AX equals 0 and AY equals 0, in other words, if we have two solutions to a homogeneous system, then two things. First of all, the sum x plus y will also be a solution. In other words, A times x plus y will also be 0. And the second thing, if we take any multiple of x, say lambda x, it will also be a solution to the homogeneous system. We'll also get 0. This one for any lambda in our scalar. Okay, so what's the proof of this? Well, if A times x equals 0 and A times y equals 0, then let's calculate A times x plus y. The crucial thing is that we know that that's A times x plus A times y. Right? That's by linearity. That's what we just proved in that previous basic formula. So now we're assuming that AX is 0, and we're assuming that AY is 0, so we get 0 plus 0, which is indeed the 0 vector. And the other one's also not hard. If we take A times lambda x, well, again, by linearity, that's lambda times A. I guess we don't need that bracket. A times x, again, by linearity. But that's lambda times 0 vector, which again is the 0 vector. All right, so that's a proof of this little proposition. That means that homogeneous equations have the property that solutions are preserved under addition and under scalar multiplication. So homogeneous systems have solutions which are maintained or closed under addition and scalar multiplication. Now there's another kind of consequence of this linearity, which I also want to describe, which sort of connects the homogeneous case to a more general case. Okay, so suppose we have the solution AX equals B. So I suppose A times X equals B, and we know that A times Y equals B. Okay, so B now, the right-hand side, is no longer zero vector, just a general vector. And we have two solutions, X and Y. So it's not going to be true that if you take X plus Y, you're going to get another solution. Okay, but what is true is that if you take the difference between X and Y, you're going to get a solution to the homogeneous equation. So then if we look at A times X minus Y, by linearity, this is A times X. Well, actually, it's, to be strictly speaking, I'll do it in a step. It's A times X plus minus 1 times Y, okay? So that's then A times X plus A times minus Y, and that's then AX minus AY. Although, you know, after you've done it once or twice, you can go directly from AX minus Y to AX minus AY. Okay, but we're assuming that AX equals B, and we're assuming that AY equals B. And so when we take the difference between those two things, we get 0. All right, so we've just proven the following proposition. That if, say, V and W are solutions to the system AX equals B, then the difference, V minus W, is a solution to the homogeneous system AX equals 0. That's what we've just proven. Okay, great. So we've done some general things, you know, having to do with systems of linear equations, connecting the row reduction and the row reduced form of a system to various consequences about having solutions existing, and whether there's one or more than one. And we've also talked about the linearity of the matrix product and sort of the implications about that for systems of linear equations. So again, we've seen that this general form of AX equals B, this very short sort of matrix kind of form, which is sort of what our preferred way of thinking about a system of equations now is. It's actually a very compact form because it allows us to conceptually make some deductions without having to write down huge numbers of things. Things are captured by the linear aspect. And it really leads us to our next topic, which is to investigate more deeply the structure of matrices and the arithmetic of matrices, which is a whole new world for linear algebra.